My presentation today will be on what are described as critical materials, and I'll describe to you what they are. And then the second part of my talk is going to be on a subset of those materials and on the recycling of what are called rare earth magnets. So my role is I run the magnetic materials group in the University of Birmingham, but I'm also the director of a centre that's focused on critical materials and how we mitigate risk. So this is the plan of my talk. I'm going to tell you first what a critical material is, tell you who cares about them, where they're from, and what they're used for. And I'm going to narrow that down into what are described as rare earth magnet materials. So I'll tell you about what those materials are, what they're used for, and then some of the challenges around recycling of these types of materials, which are known as rare earth magnets. And then I'll have some conclusions at the end. So for those that aren't aware, a critical material is basically a measure of the risk of supply shortage of a given material, which is on the y-axis over here, versus a measure of the economic importance of a material. And the EU has a list, Japan has a list, the US has a list of critical materials, but we do not have one in the UK. And we're currently writing a policy document around this for government. What it means essentially is if a material falls into this top right-hand box of this graph, it means that the material is economically important, but is at risk of short supply. And what's happening at the moment is we're moving into an era where we're shifting from fossil fuels into electrically driven applications. The implication of that is that instead of having a shortage of fossil fuels at certain times, we are likely to see shortages of key metals that are used in things like batteries and drive motors in electric vehicles. So what you see on this graph is supply risk again on the y-axis, and on the x-axis, economic importance of different materials. The ones that are in red dots on this graph are materials which are deemed to be critical. And this is the European list of critical elements. And I've highlighted a few of them right at the top of this list. So the biggest supply risk are for the rare earth elements. And they're either described as light rare earth elements or heavy rare earth elements. And these metals go into what are described as rare earth magnets. And they're an alloy of neodymium, which is the rare earth metal, iron and boron. And it's signified by NdFeB in the rest of this talk. And I'll show you what these magnets are used for. Just out of note, the other ones on the list that are highlighted are for lithium-ion batteries. Now, I'm sure you're aware of how important they'll be moving forwards for things like electric cars, but the metals that go into them that are critical are actually some of the other ones around metals like cobalt. So there are some supply crunches around some of these materials coming up over the next 10 years. Well, who cares about that? Well, if you look at where those metals are used, they're used in magnets, lighting, batteries, catalysis, photovoltaics, all those types of elements. And they're used in a huge number of industrial sectors, from electronics to automotive, aerospace, energy generation, medical, and defense. So the sorts of companies that are really concerned about these sorts of materials are listed on the left-hand side here. And these are big engineering companies across the globe. Now, if you look at where these critical raw materials are coming from, and this is from an EU report, there's huge concentrations of these elements in certain parts of the globe, and none of them really are in Europe or the UK. And that makes us actually quite vulnerable. So if you look across this list, things like platinum group metals, which are used for catalysis, are located in South Africa and Russia. You have things like beryllium in the US, but then you have this huge list of these critical elements that are located in China. And that's for several reasons, partly because they have large natural resources, but also because they've developed the technologies to extract the metals from the ground and process them into materials. And that's kind of what we're doing in the group in Birmingham. So, right at the top of the critical materials list are the rare earth metals. You may or may not have heard of them before. They form, the majority of them are in the lanthanide series of the periodic table, and they have weird and wonderful names, starting from lanthanum, cerium, praseodymium, neodymium, and so on. And it goes all the way through the lanthanide series down here. Now, the biggest market for those materials in terms of value is where they're used in rare earth magnets. And of these metals, the ones that are used in rare earth magnets are neodymium, praseodymium, dysprosium, samarium, gadolinium, and terbium. And they're all used in neodymium, well, nearly all of them are used in neodymium iron boron magnets. So if you look at where the rare earths have come from historically, so this is the year on the x-axis and the tonnage of the ore, so this is the material dug out of the ground. It used to come from the US, which is the blue region on this diagram you see here. But in the 1980s, China began to mine those materials as a byproduct of an iron ore mine. And now they completely dominate the market for rare earths. So about 90% of all rare earth magnets are made now in China. And that's actually had quite profound implications on what's going on globally. One of the things that's happened is that it's had a very large environmental impact on the countryside in China. So what you see in this NASA image on the left-hand side here, this is the largest rare earth mine in the world. You can see the town at the bottom down here. And around the outside of it, you see these kind of strange formations. And these are actually what are described as tailings lakes. Now, when you dig the material out of the ground, you have all 17 rare earths mixed together in different ratios. You only make a profit from actually about 5 or 6 of them, and they're the ones that are used in magnets. And to get the material out of the ore, you have to leach it in very strong acid, and then it goes through lots and lots of chemical processes to separate the metals. And the effluent from those processes in China has literally been poured straight onto the ground. And there's been a lot of press around this. You may have seen it in the papers. What does that look like in essence? Well, they have huge tailings ponds. You might notice there's not an awful lot growing around these tailings ponds, and that's because it's polluted all of the ground source water. So it's had a very large environmental impact on China for these materials. Now, what happened in about 2005 is China began to impose export quotas and taxes. So if you buy the material in China, it's much cheaper. And the reason for that was because they wanted to drive the manufacturing of the downstream products into China, so i.e. wind turbines and electric motors. And in 2010, they cut the export quota by 40%, and the neodymium price, which is what the left-hand graph shows you here, jumped from about $20 a kilo to $500 per kilo in 1 year. Same for dysprosium, that jumped enormously. It was up at about $3,000 per kilo. And that had huge implications globally. Obama was giving speeches on these materials. Trump has done an awful lot of work on these materials before he left office. And Joe Biden's just written a resolution around these critical elements as well, and about access. And I'll explain why people are so worried when I go through the applications. So if I move on, I'm going to talk specifically about neodymium iron boron magnets and what they're used for. But what is it? Essentially, a rare earth magnet is a permanently magnetized material. I've got one here to show you if you can see my camera. So these are rare earth magnets. You can see how strong these are. They're used in lots and lots of different applications. And basically, they're a permanently magnetized material. So if you imagine the fridge magnet stuck to the side of your fridge, and imagine it being about 10 times stronger, that's what a rare earth magnet is. So it's permanently magnetized. And the way you represent that is if you had a solid block of material and you applied a magnetic field to it and magnetized it, it would go up what's known as the hysteresis loop. And if you drop that field back to 0, where it crosses the y-axis on here, the remnants is the strength of that magnet. So that's literally how strongly bound it will be to a piece of iron. And if you reverse the field, you will go through what's known as the coercivity value. And that's the resistance to demagnetization, where you fall through the x-axis over here. So for one of these permanent magnets, based on rare earths, you have 2 really key properties. How strong is it? And that will give you the magnetic flux coming out of the application. And secondly, what is the resistance to demagnetization? So it stops it demagnetizing in the application. Now, if you look at the permanent magnet market, that's been developing over the last century. What this graph shows you here, the BH max value tells you how strong the material is. And you'll see the man-made magnets around the turn of last century were quite weak. And then through time, magnets have become stronger and stronger and stronger. They found a family of rare earth magnets in the 1970s. That was superseded by neodymium iron boron, which is the brown area on the right-hand side of this graph, the sort of light brown area. Now, why am I showing you that? Well, if you look at 3 different types of magnets on the top left-hand image here, the left-hand one is a representation of what Columbus had on board his ship. And that was for aligning the compass needles on board his ship. The one in the middle is a ferrite magnet, which is the typical material you have stuck on the side of your fridge if you've got these little holding magnets. And the one on the right is neodymium iron boron. And it develops a huge amount of flux for a relatively small amount of volume. So magnets have become much stronger through time. Now, what that's allowed us to do is to miniaturize components, and I'll show you some of those applications a little bit later. So I don't expect you to look at all of this in detail, but basically, if you want to make a rare earth magnet material, you melt the alloy, and then you break that material down to a fine powder, which I'll show you in a second in the next slide. And the magnet powder is magnetically aligned. It's then pressed into the final magnet and it's heated to about 1000 degrees C. And that's how the magnets are made that I've just shown you on screen. So it goes through this very complicated series of steps to make a magnet from an alloy, much of which is available in the UK. Now, what does that look like in practice? So what this is a magnetic aligning press. There's 2 magnets there, and you'll see them being moved off in a second. So what you're seeing in the video there is an alloy powder containing neodymium iron boron. It's dropped into a press, and then you apply a magnetic field, and you see the powder jumping around. That's to align all of the powder in the same direction, and then it's pressed into a product that's about 60% dense, and then it's heated to 1000 degrees C, and that's how magnets are made. That is exactly what my group does in Birmingham at the university. We're the only place in the UK that can make these types of rare earth magnets. So that's how they're made, but what are they used for? Well, if you look at a modern vehicle, there are rare earths all over the vehicle in things like the catalytic converter, in the LCD screen and the glass. They all have different types of rare earths in there. But there's actually over 25 motors in that vehicle which will contain rare earth magnets for something like a hybrid or electric vehicle. So they're used in the drive motor, which powers the car. They're used in generators, fans, loudspeakers, power steering units. And as you move into full electric vehicles, there'll be more and more of this material in the car. So typically an electric vehicle would have about 5 kilos of this magnet type in the application. Where else are they used? Well, all of you will be carrying rare earth magnets around with you in your mobile phones. They're used in the speakers, in the vibration motor, in the optics. And essentially what they're doing is taking electricity and converting that into motion. So in a loudspeaker, you'll have a magnet surrounding an induction coil, and it will basically repel away from the induction coil as you apply a field. But if you go to some of the really big applications, offshore wind turbines typically have about 1/2 ton of rare earth magnets in the wind turbine generator for every megawatt. So it's a 10 megawatt wind turbine generator that Siemens make will have around 5 tons of rare earth magnets in them. And you can see them here mounted on the rotating part in here. And in this case, it's the opposite. They're being used to generate electricity rather than using electricity to create motion. But huge quantities of these rare earth magnets are about to be put offshore around the UK. What do those machines look like? Well, if you actually open up all of the machine, so something like a pump or a drive motor, it would look something like this. So you'd have these kind of soft magnet laminations all stacked together. So stacked together like this. And then the permanent magnets would be mounted inside the motor. And often they're glued inside the application. And unfortunately, that makes them quite difficult to recycle. So, second part of my talk, I said I'd discuss recycling with you. And the initial part just kind of introduces the subject area. So, if you look at recycling of metals today, the critical materials often have a very low recycling rate, and that's not just rare earth magnets, it's other metals as well. Now, we import into the EU around 10 to 12,000 tons of neodymium iron boron magnets in products today, mainly made in China, but we actually recycle less than 1%. So the aim of my group over the last sort of 10 to 15 years has been to develop technologies and the infrastructure to recycle magnets in the UK. And we've been part of multiple EU projects. Now, there are lots and lots of problems in recycling of rare earth magnets. Firstly, how do you know which products has got the material in? If you took 10 handheld drills, about 70% of them would probably have a cheaper ferrite type magnet, but the high-end applications would contain neodymium iron boron. Often the magnets are very small. So the mobile phone I showed you, the magnets can be less than 300 milligrams in size. The composition of the magnets is changing. They're often coated and you've got to remove the coating. They're fully magnetized, which I'll show you the problem in a second. They're not designed for disassembly, and there's no regulation forcing them really to do it today. The economics are challenging and the supply chain in the EU is very small. So there's a lot of hurdles to overcome to develop a recycling supply chain for these materials. But for obvious reasons, it's very important. Now, if you think about where the magnets are in applications today, one of the key sectors is going to be from electronics and from vehicles. If you take a car to a recycling plant today, they will manually remove the radiator because it's full of copper, the catalytic converter because it has another critical element in it, in platinum and palladium, and that's sent off to companies like Johnson Matthey for recycling. They'll remove the tires, they'll take off the battery because they're legislated to do it. And then what typically happens to the rest of the components in the vehicle is they will literally shred the car into less than 10 centimeter pieces. So this is a shredder plant run by EMR. You can see the car going up here and it's literally obliterated into small pieces. And about 75% of that car is iron or ferrous metal, and then you cascade down through the other components. Now, when we develop electric cars, the makeup, the composition and the complexity of the metals in something like a lithium-ion battery or electric motor, it's far more complex than an internal combustion engine car. So we're going to see some really quite profound changes in the recycling technologies that will be applied. Now, if you go to one of these big recycling plants, and they're absolutely vast in the UK, and you walk around the outside of the conveyor system, you'll see things like this. See this sort of cascading series of powders down the side of the plant. What that is it's permanent magnet powder, which has resulted from the shredding process. The magnets have broken apart, and then it just literally magnetically sticks all over the plant, and you can't get it out. Just to show you in more detail, this is a drive motor. So one of those lamination stacks I showed you before. It's gone through a shredder, and what happens is the laminations distort. The permanent magnet material, so the rare earth material, is very brittle, it's the opposite. That breaks apart to a powder, and then it magnetically sticks all over the scrap and all over the plant, as I've just shown you. So if you shred something like a hard disk drive, which has got magnets in it, you can see the powder that's generated here. You end up with a big ball of material where it sticks to the ferrous components, and then it's very difficult to separate. It will never be recycled. And that brings me to the next point. If you look at a lot of applications which contain magnets, they're not designed to get the material out, and you cannot shred them. So you need some sort of disassembly to extract the material from the components. The classic example is a hard disk drive. There's one in the image here. I have one in front of me. There's actually magnets in this voice coil assembly, if you can see my camera here. So if you ever want a strong magnet, you can dismantle an old hard drive and there'll be magnets in there. And there's also magnets in the spindle motor in here, which spins the disk around. If you go to automotive, there are magnets in the drive motor. You can see the dark material here. That's neodymium-ion boron, but they're glued into the application. Magnets in mobile phones are very small, and these are some of the canisters from wind turbines. They're up to 7 kilo blocks of material. Completely different problems with all of them, ranging up to safety issues for these types of magnets for wind turbines. If you get 2 of those magnets stuck together and you're in the middle, you will be very, very badly injured because the force of the magnets sticking together is just so high. So I'm going to explain a little bit about what we've been doing in Birmingham to tackle all of these problems around sensing, separation, extraction and reprocessing of these materials. And we've been doing that from like 1 or 2 gram samples up to a very large plant that we're developing in Birmingham. So the first problem we looked at was, how do you work out where magnets are in waste streams? And one of the ways we did that was we realized above things like electronics, you can magnetically detect the magnet inside the component without opening it up, which tells you where the magnet is in the waste stream. And you can see that in this image on the right here. So these are the magnetic flux above a drive. And with a European partner, we started to develop a line where you put the hard drives on here onto a conveyor system. Underneath, there's an array of magnetic sensors. Above it, there's an optical camera, which is drawing this line around the hard drive. And that information is relayed to a robotic system. And what the robot's doing is it's essentially working out where the magnet is in the drive. And then with a very clever piece of software, it's guiding the hard drives into a cropping system, and it's just cutting the corner off the drive. So it's removing the magnet containing component. Why is that important? Well, it concentrates the scrap where the magnet's contained, because the magnet's just in the corner. And the drive, the actual information on the drive then goes off for shredding, so the data is secure. So that's where the magnets are in the video here. And that's what we're processing next. So what we then did is we developed a technology using hydrogen to separate the magnet from the waste stream. And there's a patent on that, and it's being scaled with a company called Hypermag, and I'm one of the directors of that company. So you may think, why are we talking about hydrogen? Well, if you look at a rare earth magnet and you expose that material to hydrogen, the video on the right-hand side shows you what happens to it. So the hydrogen enters part of that structure, what's known as the crystal structure. And as the hydrogen is absorbed by the material, it expands. So it's a bit like corrosion, where you have oxygen going into iron. And that generates very high force. So as the magnet absorbs the hydrogen, it starts to crack apart, and it develops a powder. It literally breaks the entire magnet apart in about 40 minutes. You may ask, well, why is that useful for separation? Well, the first thing it does is it demagnetizes the powder that's generated, and it makes it much easier to remove. And then if you process something like, this is the voice call assembly out of a hard disk drive, top left. If you process that in hydrogen, the coating peels off the magnet, and you have to remove that for recycling. If you can see my cursor, you can see there's 2 glue tabs that used to hold the magnet into the application. It liberates it from the glue, demagnetizes the powder, and then we can liberate that powder from the electronics. And we can do that to a very high purity, which I'll show you in a second. So we've been gradually scaling those processes up. So what you see in this image here is a 300-litre hydrogen reactor. It's inside there's a porous drum. You may recognize this. It is literally a washing machine drum. Inside there, we can get 500 corners from the hard disk drives, which contain the magnet. So that's from a recycling plant in Sweden. We put it inside the drum, we close the lid, we evacuate the air, because you can't have an air-hydrogen mixture. And then we expose all of those corners to hydrogen. After a couple of hours of exposure, all the magnets inside the components are broken down to a powder. Then we spin the drum inside the reactor, and the powder drops out and is collected down the bottom here. And this is what it actually looks like. So this is a magnet breaking apart in hydrogen. You can see the coating peeling off the surface. You'll next see the voice coil assembly from the drive reacting in a similar way. So that's normally in the corner of the hard drive, this assembly. This process where the drum's rotating, you wouldn't normally see. And then at the bottom there, we will collect about 5 kilos of powder from 500 hard disk drives. And you see here, there's bits of the coating still left in the powder. Now that powder is an alloy containing hydrogen. So a lot of the work in magnet production has already been done. What you see in the powder are bits of plastic, some screws, bits of the nickel coating, which is on the surface of the magnet. But because the powder is so brittle, because it's got hydrogen inside it, we can sieve that down to 90 microns, and only the magnet powder will actually mill down. It breaks apart much faster than the other components. And in essence, what we end up with is an alloy powder, very high purity, and it's of a purity where I can literally remanufacture a magnet from that alloy powder. And there's lots and lots of ways you can remanufacture that powder. I'm just going to describe one of them at the end of this talk. But essentially, if you go all the way back to the mine, you dig the material out of the ground, it goes through a chemical process, which is the one that produces the effluent that I showed you earlier. You then strip the oxygen away using electro-refining, which is similar to aluminium production. You cast an alloy, and then you go through that complicated sort of flow diagram I showed you earlier to make a magnet, and then it goes into the component. Now, the conventional way of recycling a magnet when it's done at all is to pass it all the way back through solvent extraction to a chemical process. And the environmental burden of that's very high. So what we've been doing is, because we can strip it out very clean, we put it straight back into magnet manufacturing or into cast alloy production. What does that look like? Well, this is our hydrogen reactor. We purified the powder. We literally blend the powder with a primary alloy. So we have a mixture of the two. It's then pressed, just like the process I showed you earlier in the die set. Magnetically aligned, we then heat up to 1000 degrees C, and we can recycle a magnet over here. And it massively reduces the cost and the environmental burden of production. Now, just to give you an idea what the properties are like, this is the second quadrant of the hysteresis loop. So if you remember where we cross the axis on the y-axis, that's the strength of the magnet. And then the x-axis down here is the resistance to demag. And essentially, we can make a magnet which has got the same strength as a primary material. So what this graph shows you here, the blue line is a magnet made from a primary cast alloy. So that's a mined material, not recycled at all. We've then blended in different ratios of recycled powder from the process I've shown you, 25%, 50%, and 75%. And it basically tailors what's known as the coercivity down here on the x-axis, which is the resistance to demag. What should you take from that? Well, you can make a magnet which is almost as good as a primary material, but with a massively reduced cost and environmental burden. So what are we doing next? Well, we're taking those processes to scale. The hydrogen process has been licensed to a company called Hypermag Limited with investment from a junior miner. We're building a magnet processing facility at the university in this building. So the whole of that building's been developed for this process. And we're part of a very big European project that has 20 partners. So it has the whole supply chain in there right across the EU. So from recycling company all the way up to magnet manufacturers. And what we aim to do is we are going to scale that process at a site which is about 4 miles from the university up to 100-ton level, to give you an idea, with Hypermag. And it's going onto this site. So the whole of this site at the Tyseley Energy Park is being used for clean energy development and recycling. So there's bioproduction of energy. There's a hydrogen production facility on site from waste, and that will all be used in the processing of magnets on this facility. So I'm running out of time. I'm at my conclusion. So what are the messages you should take home from this? Well, there is a large redundant stock of NdFeB and spent electronics and a lot of other end user markets, and that could be used as a price stabilizer. So to avoid these very high price spikes that I showed you earlier. The challenges for separating the materials shouldn't be underestimated. One of the big costs really for recycling is how you separate the material from the components in the first place. Scrap magnets only contain typically 2 to 4 rare earths, and it's about 30% rich in material in these rare earth elements. That's far higher than you would dig out of the ground. And the other thing which I failed to mention earlier is that a mined source of rare earths typically often contains radioactive elements. And obviously you avoid that from a recycled source. Hopefully I've shown you that hydrogen's a very nice way of separating the material from the waste stream, and it's a very low energy route with a low environmental footprint for reproducing a magnet. And then finally, your choice of reprocessing route, because there's actually about 5 or 6, is a trade-off between the quality of the magnet you want to produce and the properties you're trying to gain versus the cost and the energy penalty you're willing to pay for making the magnet. And finally, I'll leave you with some acknowledgements. My contact details are on here. Obviously, a lot of the work was done by the members of my group. Typically, we have about 20 people working on various areas of magnet production at Birmingham, and then I've acknowledged some of the projects. So I will stop there and leave you to ask questions.
Well, thank you very much, Alan. That was absolutely fascinating. I love the way that you use the drum from a washing machine to help recycle magnets. I think it's great. We've got a couple of questions in the chat. First one is, are these elements poisonous to humans? I think this was asked around the time you were showing the lakes in China.
Yeah, not necessarily actually, but the chemicals that are used for the extraction are, because they'll use things like hydrochloric and sulfuric acid, for example. So the separation processes are a problem, and often because the ore body quite often has things like thorium mixed in with them, which is radioactive, it's the other associated elements that are actually a greater risk than actually the rare earths.
Okay, yes. So they're quite dramatic, those lakes.
Well, yeah, I mean, you've got to be, I mean, I have to be careful when I give this talk, because bear in mind that that facility produces 40% of the world's rare earths. So the mining capacity for those materials is very, very small compared to if you look at something like copper or other metals. So the environmental burden is tiny, really, compared to the environmental benefit that you see from those materials, because if you use them in a motor, the efficiency gain can be anywhere between about 5 and 15%. And if you scale that for electric vehicles, the CO2 footprint of that will be absolutely vast if you don't use it.
Yeah, this is this whole sort of considering all the every element of the whole cycle of the material, really, isn't it?
Yeah, it is. I mean, you know, obviously they should be mining it in a way which is much more environmentally friendly, and you know, there's evidence to say that that's being cleaned up in China, but you know, it depends who you ask that question of. Let's put it that way.
Yeah. Brilliant. And the other one in the chat was that someone's heard that there have been lots of car part thefts recently. Is this for the rare earth magnets?
No, no, it's not. It's for the catalytic converters. So people will remove the catalytic converter because there's palladium, rhodium, and platinum in them, which is actually on the critical materials list. It's one of the elements which is in a shortage of supply. So the value of that metal, to put it in perspective, I think it's either platinum or palladium's, you're talking like £26,000 a kilo, whereas a rare earth magnet would be, or neodymium would be about £100 a kilo, something like that. So there's a huge difference. But however, having said that, there's only about 2 to 5 grams of it in a catalytic converter. So no, I don't think the car thieves have cottoned on to the fact that there's a value in that material yet.
Oh, fantastic. There's another one's come through. Is anyone working on? Oh,
yeah, I just seen that. No, well, yes and no. I mean, we've done surveys of recycling plants. So there's a guy at Birmingham that basically surveyed all the critical materials in every part of a shredding plant. Because what happens is you shred the material, and then it goes through magnetic separation to remove the ferrous components. Then it goes through things like electrostatics and size separation to remove things like the polymers. So it kind of cascades through the plant, and they've sampled where the rare earths are all the way through the plant. The problem is that by the time it ends up in the fine fraction, which is typically where it ends up because it breaks apart, it's so heavily contaminated with other elements that it would be uneconomic to extract it. So they will, if it ends up in that plant, it will, unless the value of it's way above the current value, and I'm talking 10 times higher, then it will never be recycled. So you have to avoid shredding.
Yeah, Fascinating. I was really impressed with this robot setup, actually, because one of the sort of discussions we were having on a panel discussion earlier was about sort of composite materials and how difficult they can be to recycle, but to sort of like be able to identify the one bit of a component of a device to then recycle. So that's really good.
Yeah, I mean, we have another project that's looking at lithium-ion batteries. So it's probably the biggest in the UK. I think there's a project called Relib, which is part of the Ferrite Institution. And they're looking at similar technologies for lithium-ion batteries. And for me, that's a no-brainer because they're so dangerous to handle. I mean, I've got another video, one of my other talks, where somebody accidentally shreds one of those batteries off a lawnmower and it blows up the entire top end of the plant. Oof. Because the energy density is so high in those types of applications. So for recycling, there are some really key applications where not just that it would reduce the cost and the manpower cost, which is the biggest cost in the recycling process often, but it's also the safety aspect of it as well. And the disassembly of wind turbines, man, those magnets are so strong that they're assembled with robots because they're too dangerous to handle.
Oh, wow.
Yeah.
Well, there's a couple in the Q&A box now.
Oh, there's another question here around legislation. Do you want me to address that one?
Yeah, go for that one.
So the question that's arisen is around, are governments looking at legislation to recycle these materials? Sort of. At the moment, the legislation around the vehicle is based on the weight of the car. So you have to recycle 95% of a vehicle, which they can do easily with internal combustion engine cars now, just with the processes I've shown you earlier. What's happening at the moment is governments, and particularly in the EU, are looking at new regulations for things like lithium-ion batteries. So a new regulation came out in December or January, I think it was, where there's a weight target for the individual metals in a lithium-ion battery. So that includes cobalt, nickel, lithium, and manganese. And there's a target set by 2025 and then 2030. Now, I think what they're likely to do is look at that as a blueprint for the other electrical systems, including the drive motor. And so if they do that, that would be a real game changer if they had a recycling target on rare earths. But they've got to be really careful, because if you imagine a mobile phone with 200 milligrams of material in there, it's incredibly difficult to extract that. So I think what they're likely to do is to set a power rating on a motor, and everything above that power rating, above a certain size, that you'd have to recycle it. So kind of, is that happening in the UK? It depends on if they take on that EU legislation, but I think it's more than likely, because the car companies will have to sell into those markets.
No, okay, fantastic. Then we've got the two that are in the Q&A box. First of all, are normal magnets also hard to recycle?
It depends on what you mean by normal magnet.
I'm assuming that the sort of like fridge magnets kind of thing.
Yeah, fridge magnets are never recycled. I mean, fridge magnets are basically what's called a ferrite material. So they're basically rust. So it's iron, oxygen, and then they're mixed with strontium or barium. And the value of that is so incredibly low that they're never recycled. So that stuff you see on the side of the plant is a mixture of rare earth magnet and ferrite. But no, none of it will be recycled.
And the other one in the Q&A is, are electric cars good for the environment because they do use rare earth magnets?
Well, that's a multifaceted question. Yeah. Right, let me go through that one. So basically, if you look at a car, there are graphs that will show you the environmental burden of an electric car versus an internal combustion engine car. So if you just look at the CO2 impact of an electric vehicle, there's a crossover point. What I mean by that is that the embedded carbon in an electric car is higher than an internal combustion engine vehicle. So you expend more CO2 making an electric car. But then obviously when it's running, you're not using fossil fuels. So there's a crossover point, and lots of people will argue and give you different figures. But I've seen where it's quoted that it's around sort of 25,000 miles of running the vehicle. So that's the first thing. Now, the rare earth magnet, if you use that in the actual motor of an electric car, as I said earlier, it's 5 to 15% more efficient. And that might not sound a lot, but in terms of efficiency of machines, that's enormous. So if you imagine, if you don't use that magnet in the motor, and it is less efficient, then that impacts the CO2 footprint straight away from the vehicle. But it also means your battery's got to be at least 5 to 15% bigger. And that impacts all of the embedded CO2 going into the application as well. So yes, those types of elements and these critical elements are essentially the building blocks of what will develop into clean growth.
Yeah. And another one that's not there, but I've just come to my attention was you were saying about the size of the magnets needed in wind turbines.
Yeah.
Will the sort of availability of the rare earths eventually limit the amount of the number of wind turbines we can produce?
Well, yeah, this is
only a finite amount.
Yeah, this is something I haven't touched on. Right. Just to explain this thing, rare earths are not actually rare. It might seem like it from my talk, and I should have touched upon this. So, like neodymium is as abundant as tin, so it's not a scarce element. What is scarce is the processing capacity and the willingness to live with the environmental burden of production. Okay, so if you look at the capacity in China, there is easily enough material in the ground to process into a magnet. The problem is that there's basically state level control of the production in China. And because essentially you can make the magnets so cheaply in China, there aren't many competitors globally. There's only really Japan that still makes the material. Okay. So the risk is actually if China cuts off the supply. You could start developing it elsewhere, but to get a mine running takes at least 10 years, typically no more like 15 years. So you've got this huge lag time. So you've got this kind of demand and use cycle, which may outstrip capacity of refining rather than what's in the ground.
Okay, fantastic. Well, thank you very much. I can't see any questions, and I've realised yet we've sort of had nearly 15 minutes of questions. So if there's no other questions, I'd like to thank you very much for your talk. It was fantastic. And yeah, if you don't mind, it might be available on the YouTube channel next week, if that's okay.
Yeah, no problem.
Fantastic. But I'd like everyone to sort of join me in thanking Professor Allan Walton again. And now we're going to have a quick break.